So today we continue with now it says extending subtraction to rational numbers. So it says how is a chip model or number line used to determine an algorithm for subtraction? So in 2.1 we've spent a lot of time with addition, right? So it says in 2.1 you've learned about the commutative property, right? That's where we can flip our two numbers and still have the same answer, right? Opposites are also called additive inverses. Remember, we learned that too. When you add a number and you add its opposite to it, it is always 0, right? You also learn the additive identity, which is when we add any number, we take any number and add 0 to it, it's always the number you're adding 0 to, right? Because you can't gain anything when you add nothing to something, right? That makes sense, right? All right. So one way to think about subtraction problems is to take away objects from a set. So think about this. It says Kim had 9 DVDs. She sold 4 at a garage sale. She now has 9 minus 4 equals 5 of those DVDs left. So this is how they used it on the chipboard, right? Here's the 5. They took the 4, slid it away, and you got 5 left, right? Pretty easy example, right? So think about this one now. Otis earned $5 raking leaves. So here's his 5 chips, right? He wants to buy a bike that costs $7. His older sister puts 5 black chips on the table to represent the money Otis has. So what is the value of Otis's board? What's the value of Otis's board, Blake? $5, right? Yep, positive $5. Right? That's what he has. Okay? Now the story continues here, so Otis's sister asks, how much more money do you need? So Otis replies, I could find out by taking away 7, but I can't take away 7 because there aren't 7 black chips on my board. He only has 5, right? This part here is what he originally had, right? His sister adds, so this is kind of what his sister adds right here. His sister adds 2 black chips and 2 red chips, right? Because now she added 0 to 0, right? But now he's got 7 black chips. So is the value of the board the same with the new chips added? Is this value of the board the same? Is it still technically $5? Yeah. Because again, they added the zeros, right? 1 black chip and 1 red chip cancel each other out to be zeros. So yes, it's still the same. So how does this help Otis find out how much more money he needs? How does it help him? If this is what he has, right? This gives him 7 black chips, right? So how many more chips did he need?
Well, it takes away the 7 black chips, he'll have the 2 red chips left because he needs.
Right. This shows him that he needs 2 more black chips to get his bike. All right, his $7 bike. Can't be that great of a bike for $7, but okay. So you see how we use the chipboard for that? Okay. So let's start getting into it. So Ben takes $75 from his savings account. He goes shopping for school supplies and has $35 left when he is done. To figure out how much money he has spent, he draws the following number line. So there you see it, right? So how much has he spent? So we got to think about, we go from 75 to 35. Look on the number line. Lily. How much? Look, where's that number line ending? It ends at 35, right? So if we have 75, right, and these numbers are 10, which means if I go halfways here, That distance is also 10, right? So 10, 20. So how much money has he spent? Yeah, he spent $40. He spent 40 bucks. So now it says, how should Ben label what he spent to show that this is money that he no longer has, right? So if I label this graph up here, right? Here's your minus 40. How can I write that in a number sentence? How can I put this scenario into a number sentence? So he's left with $35. Sal.
35 minus 35, 45, 40 equals 35.
Right. Because again, we started here. We took away 40 to get to there. Right? All right, so part B, we're going to pause this and I'm going to turn you loose for a few minutes. All right? You can either use a number line, so draw a number line, or you can use the chip model. Chips are still up here. And I want you to find the differences in each of the given groups. So now we're going to be working on subtraction. So we're going to take about 5 minutes for you to work on this. So either grab a bag of chips or use a number line. Okay, we're going to give you some time to work on this. All right. While we go over this, also try to keep in your mind this. How does using the chip model when we're subtracting kind of compare to when we added? So, for example, in group 1, we'll start with group 1 first, right? If we have 12 black chips, so there's 12, right? And we subtract 8, right? So we're going to take this 8 and we're just going to get rid of them. What's left? 4, right? Now again, how can we show this using a chip model? If we start with -5, what color chip is that? Red. So there's 5 red chips, right? And we have to take out 7. Well, we don't have 7 red chips, right? What has to happen, Elena?
You have to cancel take a red and black chip and cancel it out.
Right, we have to add 2 red chips and 2 black chips, right? Remember our zeros? Right? Because now we have 7 red chips, right? And if we get rid of these guys, what's left? 2 black chips, which is the actual answer is 2. How many people got 2? Excellent. No, not 12. It's not -12, it's 2. Put all 4 legs in the ground. All right, now again, 4, -4, which is 4 red chips, right? I'm going to get rid of 2 of them. So those goes away, right? What's left? -2, right? 2 red chips are left, right? And 2 red chips are worth -2 in value. Now the next one is +2, so that's 2 black chips, right? And I'm subtracting 4 black chips. So again, what has to happen? Because I don't have 4 black chips. What do I have to do to my chip model, Robert?
Add pair of
Right, I got to add 2 black and 2 red, right? Because it's still our value is 2, right? But now when I take away the 4 black, right? What's left? 2 red, which means our answer is -2. All right, so now let's look at group 2. So in group 2, we started out with 12 black chips. 2, 3, 4. And I'm going to subtract 8 red chips. I don't have 8 red chips, do I? So what has to happen?
You have to add.
I got to add 8 red chips, right? But then I also got to do what? 8 black, right? Because this whole group here has to still equal 0, right? Now, if I get rid of that 8, right, goes away, what am I left with? 20. How many people got 20 for that one? Awesome. Okay. So again, remember, you got to add those zeros. You can't take away something that you don't have. Okay? Excuse me. It's the time of the year where everyone starts coughing, right? All right. So now, I have 5 red chips, right? Because -5 is 5 red chips. And I have to subtract 7 black chips. I don't have 7 black chips, right? So to do that, not only do I have to add 7 black chips, I have to add, right, because again, they have to be 0, right? So again, this group to my right is still worth 0, right? But now I can get rid of my 7 black chips, right? So when these guys go away, what's left? How many red chips? 12. So what's our answer? -12. How many people got -12? Are you starting to see what's happening here? Think about it. If you show this on a number line, right? If I'm at -5, here's 0, and I subtract a number, which way am I going? That way, right? I'm going that way 7 units. So 6, 7, 8, 9, 10, 11, 12. That's how you can show it on a number line. All right. So 4 red chips. I want to take away 2 black chips. I don't have 2 black chips. So we have to, Robert? Right, 2 black and 2 red. Because again, this is still 0. So we're starting out with 4 red chips, right? But now when I take away these 2 black chips, see you later, what's left? 6 red, which is -6. Okay? And then last but not least, if I start with 2 black, and I got to take away 4 red. I don't have 4 red. So again, we got to add 4 black and 4 red to help us, right? Now, when I add 4 black and 4 red, and I take away these 4 red, what's left? How many chips? 6 black, which means the value is 6. So look what you notice here. Anytime we had the double negatives here, 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 and here, okay, our numbers got bigger from where we started. Didn't you see that? Right? Because we started at -4 and ended up with -2. Isn't -2 bigger than -4? Isn't 2 bigger than -5? Guys, we're not playing the chips. Isn't 20 bigger than 12? So we didn't really end up subtracting. We really ended up adding because we had to add these extra chips in so we could subtract, right? And then every time we just subtracted a positive number, the numbers got smaller. Do you notice that? So if we go to our little summary here, so in group 1, the signs of the numbers subtracted were the same. Did you notice that in group 1? We subtracted a positive number from a positive number, a negative number from a negative number, a negative number from a negative number, and a positive number from a positive number. So all the signs were the same in group 1. Did you see that? Now in group 2, what'd you notice? The signs weren't the same, were they? They were opposite. They were different signs. So I can pretty much write the same thing here. The signs subtracted were different. Or if you write opposite, same thing. They were different. You subtracted in the first one a negative number from a positive number. In the second one, you subtracted a positive number from a negative number, and so on. So we want to come up with some kind of a strategy, an algorithm for what this is, all right? So if the first number is greater, meaning it's the bigger number, like for example, 12 was bigger than 8, right? When we subtracted 8 from 12. So the first number is greater than the second. Okay? Your answer will be, what happened when we subtracted 12 from 8? 12 was bigger than 8, right? Our answer ended up being positive. Okay? Now to turn that around, if the first number is smaller than the second, what happens to our answer then? Hello, wake up. Your answer will be negative. Because again, when I take away a bigger number from a smaller number, we go negative, right? Because we don't have enough positive numbers to keep it positive. It goes negative, right? And then I'm going to put a little tidbit in here. Actually, I'll write it in a different color. That way it stands out a little bit. And I'm going to kind of write an example here for you, too. So adding the opposite will give you the same answer. And what that means is this. We had some problems where we took away, right? We subtracted a negative from a positive number, right? And we got, the answer here would be 6, right? So it's the same as saying this. Adding the opposite of negative 4 is 4. So when you subtract a negative, it's the same as adding. Okay? Same thing. So when you see that double negative, what you're really doing is adding. Right? Every time in group 1, when we subtracted that negative 5 minus negative 7, we ended up with 2. Right? So that's kind of a special rule there. All right. I want to give you about 7 minutes to work on parts C and D, because you should really blow through part C really fast. But then in part D, I want you to tell me whether these two expressions are equal. And then, of course, if they're not equal, tell me why. And you'll find out pretty easily if they are or they aren't. Okay? So I'm going to give you about 7 minutes to do part C and D. So find out those subtract using our little algorithm, our strategy that we came up with. I want you to solve these 3, and then look below and tell me if these two expressions. So if you were to subtract 3 from negative 2, is that the same thing as adding 3, or subtracting negative 2 from 3? Right? Basically, what are they doing down here in D? They're seeing if the commutative property works for subtraction, right? So let's see what happens. I'm going to pause the video again. So if we use our algorithm for the first one, okay, is the first number, okay, smaller or bigger than the second number? It's smaller, right? So if the first number is smaller, then our answer is negative. So if I subtract 3 from negative 1, I get negative 4. And again, if you do the chip models, if you got one red chip, you got to add 3 red and 3 black, right? Take away the 3 black, you got 4 red, right? Now, look at the second one. Is this number bigger or smaller than what we're subtracting? Bigger, right? So when the first number is greater, your answer will be positive. So 8 minus then a minus 3. What was our little rule down here? Right? In green, you can add the opposite. What's the opposite of negative 3? So instead of saying minus a minus 3, you could actually say 8 plus 3, which is 11. How many people got 11? Very good. You followed the rule. Now, this is almost like the same thing, right? Negative 10 minus a minus 7. So it's like you can say in plus 7. So think about it. What's negative 10 plus 7? It's still negative because the first number is smaller than the second number. So what's the answer? Negative 3. All right, going to the bottom. So can we use basically the commutative property in subtraction? Well, if you did these, right? If I take negative 2 and I subtract 3 from negative 2, what do I get? Negative 5, right? Now, what happens if I do this one here? Right, this is positive 5. So these two don't equal each other, right? So that's a no. What about this one? If I subtract negative 4 from 12, that is really what? 16, right? Because remember, you can say plus 4, right? And negative 4 subtract 12 from negative 4, we get negative 16. Well, that doesn't equal each other, so that's a no. So far, we're 0 for 2, right? You think any of these are going to work? Well, if I do this one here, this becomes 5. And this one here is negative 5, so that's a no. And if I subtract 21 from 45, that's 24. And if I subtract 45 from 21, that's negative 24. So those don't equal each other. So this is a big no. So the reason that is there commutative property of subtraction? So obviously our answer is no. And the reason being is, it says because the order of the numbers when subtracting matter. Because you're either going to get a positive or negative number, right? It didn't matter when we added. Whether I add 45 to 21 or 21 to 45, we get the same number, right? However, when we do that subtracting part, then that matters because you're either going to get a positive number or a negative number. Okay? So there is no commutative property of subtraction because it's just not going to work out. So if you notice, I got the summary here on the back page. So this is kind of what we got out of this section, right? Notice it's on your back page. You don't have to write this. So when subtracting numbers, when the signs are the same, subtract their absolute values, right? So the first number is greater, your answer is positive. We had just written that, right? If the second number, turn off your conversations, please. If the second number is greater, your answer is negative, right? We talked about the double negative, right? It says you can use a number line or chip model. We kind of figured that out to help finding the differences, right? All right, so we finished. This is kind of part one. We'll finish part two tomorrow. Okay.